Indeed, I changed a bit the title with respect to a couple of months ago. So I want to tell you about some recent things that we understood about how algorithms behave in high-dimensional non-convex landscapes, work done with a bunch of students and collaborators. So, this thing was working. So the kind of main overarching question that I'm thinking about in different contexts these days is this generally question that which high-dimensional data processing problem that, if set as an optimization problem leads to a non-convex objective is solvable close to optimally retractable algorithms. So I guess many of the questions that you are asking and also, is a variant of this question. And in particular, if you look at widely used algorithms for non-convex optimization, how do they compare? So that's, of course, very, overarching many problems. So to tell you kind of the way we are thinking about it, I start with a kind of typical example of a problem that I am thinking about, which is this kind of a card game. So I have a number of people in the audience, like here, and I have a deck of cards. And each card has either +1 or -1 written on it. They are randomly shuffled, roughly the same number of +1s or -1s. And now what I do, I deal one card to each of you. The important thing is that I don't see the cards that I deal to you. That will be the game between you and me. My goal will be to guess which card everybody has. But since I'm not a magician, I'm a mathematician or physicist, I need to have some information about what I gave you. So the information that I collect will be the following. I pick a pair in the audience, pair of people, and I ask them the following thing. I hand them a little calculator that generates random Gaussian numbers. For instance, oops, this is advancing. Not familiar with this. Okay, here I am. I thought there was a pointer. Yes, this is a pointer. And I tell them to generate a random Gaussian number with 0 mean and variance, capital delta here, and give me this number plus 1 over square root of n, where n is the number of people if their cards are the same, and minus 1 over square root of them if their cards are different. Okay? And they are not cheating, they are playing this game, and I ask every pair in the audience to give me such a number y, and then I collect this number y from every pair, so I end up with this symmetric matrix y, and my goal is from the matrix y to recover who had which card, which I will be able to do up to a symmetry, right? At best, I will be able to split the room in 2 groups. I have no information about which group has +1 and which one has -1 because I only measure the products. Okay. So that's my game. So how, if you give such a problem to some smart student in some data science related course, what will he or she do? She will remember something that is called PCA, the principal component analysis, and realize that the matrix that I collected y is actually a random matrix Z plus a rank 1 perturbation. If the random matrix Z was not there, the spectrum of this matrix Y would just be 1 non-zero eigenvalue and all other 0 eigenvalues. And if the noise is there, this property kind of survives a little bit in the spectrum, and there are very well-known results about associated phase transition that state that as n is large, when this variance of the noise is bigger than 1, then the correlation between the ground truth value of the cards and the leading eigenvector of this matrix is close to 0, goes to 0 as n goes to infinity. And if this noise is smaller than 1, then the correlation is positive. So I'm doing some, something useful for splitting the people in the right groups. So this is nice, but I like to play this game of having an optimal algorithm. And this algorithm is not optimal in the sense that it's not splitting the group in such a way that the number of correctly assigned people is optimal. Okay? So this one is suboptimal. So what is the optimal algorithm to solve this problem? This we know very well. That's based on Bayesian inference. And what you need to do is the following. You still assign the cards the plus minus ones, and you write what we call the posterior distribution of what were the cards given what we observed. which is just the normalization times the prior on the cards, saying we had plus minus ones and roughly the same probable ones. And here is the product over all the pairs, saying that what I observed is the product of the cards divided by square root of n with the Gaussian variance, because that's the game we played. So the likelihood here is this Gaussian. And now the optimal way to solve this problem, in the sense that it really maximizes the number of correctly assigned people, is that we need to compute the marginals of this probability distribution, meaning that we need to sum over everybody else except, say, Luigi, to compute which card Luigi has. And that's a sum over exponentially many terms. So this is a perfectly valid optimal way to solve this problem, but since it involves exponentially costly sum, it's computationally costly in the worst case. So that's the drawback of this method. It happens when we write this posterior and look at it from the view of statistical physics as the Boltzmann measure, it actually ends up to be the Boltzmann measure of a Sherrington-Kirkpatrick model that in physics we study since many decades. So that's the reason why we know how to say something about it since a long time. And notably, we know how to, this should be working. That was, okay. I will be careful with that. And notably, I somehow jumped 40 years of progress on this Sherrington-Kirkpatrick and related problems. What we know these days to say about a problem like this, I summarize it in 3 points. The first point is that we can solve a much more generic problem than the game that we are playing here. Notably, the cards do not need to be plus minus one. I can have a generic distribution of real valued cards in the deck, and this is, the solution is still valid. The noise doesn't have to be additive Gaussian. It can be any probabilistic channel from the product of the two cards to what I observe. And I don't have to be observing pairs, but I can be observing p uples, leading not to a matrix, but a p auto p tensor. So that's about the first point. The second point is that 40 years ago, the solutions in the physics papers of what is the optimal performance of this Bayes optimal estimator was derived using non-rigorous methods called the replica method, cavity method, and related. For the special case of these Bayes optimal estimators, their performance these days, we know how to prove that those formulas are indeed correct rigorously, so that's the second point. And third, so far it's nice that we know how to describe what is the optimal performance, but do we have an algorithm that is actually computing it in less than exponential time, in say linear time in the input size? And that's this point about the approximate message passing. So I just show you 2 slides per point, and then I move somehow to the main part of the talk. So this is a summary. So the first point. So here I'm just showing you how this posterior probability distribution changes if you have a generic prior on the cards and generic output channel on what I observe given the product of the two cards. And I can, this matrix that I observe in our game was symmetric, but I can also make it asymmetric if I have, in a sense, bipartite Sherrington-Kirkpatrick model, if you want this case. And this case corresponds when I measure the p uples instead of pairs, and that leads to the tensor, case. And in statistics, people call these kind of problems the low-rank matrix estimation problems. So that's like generalization of our game. And the goal is still the same. We observe the y, and we want to infer back the x, or in this case, the u and v. And here is just a list of applications or problems that can be formulated in this framework. Okay, I need to go back. That can be formulated in this framework, so maybe each of you has there some keyword that they are familiar with, or if not, don't worry too much. I will not be going into details. That's just that it's relevant to many problems that you can encounter. About the second point, about what can we prove here, really. So to state it, what we can prove is that this logarithm of the normalization in the posterior, if we divide by the size of the system, in the large and limit concentrates around the maximum of a function, that is this function here, that depends on one scalar parameter m. And to understand it, there is the m, there is the delta, there is x and y are scalar variables distributed either from the prior or a Gaussian. And there is this Carl Z, which is defined as a normalization of a probability distribution that you obtain if you multiply a Gaussian times the prior. So it's a particular scalar probability distribution. What we want here is that we had this n-dimensional problem where n was large, exponentially costly to compute anything straightforwardly. Here we formulated it via a maximization of a single scalar variable function that depends, on expectation over scalar variables, so some double integral there. So this is something we can easily evaluate compared to the horrible n-dimensional problem. And, why are we interested in this, what we call the free entropy? Well, that's a generating function for anything like interesting. So notably, part 2 of the theorem is that, I will get crazy with those. Maybe I should just be switching here. So what we can directly derive from that, if we take the m at which this function is maximized, then this leads to the minimum mean square error that is achievable by this base optimal estimator. So it directly translates into what is the optimal error. So that's why it is kind of interesting. So, and the third point about these approximate message passing algorithms that match the optimal performance in certain well-defined regions. So this is just a few equations summarizing what such an algorithm does. It's an iterative algorithm that iterates estimates of the marginal means and their variances via a set of equations that, this function f is again related to this product of the prior and a Gaussian. And the arguments a and b are updated this way, where you have the previous estimates a and v, the matrix that we observed, and these deltas and n's here. So it's an iterative process that we initialize randomly, iterate, hopefully it converges. So it goes back again to some works in physics of the Thouless-Anderson-Palmer TAP equations that some of you surely know. And there has been a recent line of work on these algorithms. This is just a small selection of related papers. What's really magical about this algorithm is the following thing, that despite it being an algorithm that runs in high-dimensional space, right? The dimension here is the number of parameters, the n, and it's a complicated iterative process where correlations are created pretty much all over the place, we can trace rigorously the error that it does at every given step. And this is it's very simple. It's called a state evolution. Proving it is maybe less simple. But the result is the following, that we need to take the same function that we had before in the theorem that a priori was not at all related to the algorithm, but this claim actually tells you that they are related. And before the optimal error, we got it by evaluating the global maximum of this function. And the error the algorithm is reaching is the local maximum of this function that has the worst error. Okay, so the same function tells us what is the optimum of performance and what is this particular algorithm achieving. And also, of course, if this function has a single maximum, then they both agree, and the algorithm is matching asymptotically the optimality. But if the function looks something like this, then the algorithm is a suboptimal with respect to the optimal estimator. So what do we get if we evaluate this function in some particular case? So an interesting case here is what's called sparse PCA, sparse principal component analysis in statistics. That's a simple variant of our game, where in the deck I still have plus minus ones, but I also have many zeros. And the row is here 9%, 8%, something like that. That's the number of non-zeros in the deck. That's a fraction of non-zeros in the deck, okay? So most of the deck is zeros. And the graph here is showing us the fixed points, the local maxima or minima of the function of this free entropy function. In the light blue, that's the performance of the PCA. And somehow if we translate the claim of the previous slide, so I will pick this value of rho to translate it algorithmically, what it actually means it means that this diagram splits into 3 regions. So on the x-axis here we have the noise, so larger noise is harder. And here we have the overlap with the ground truth. So larger overlap is better, but also harder to get. Okay? So the purple region is the one where it is impossible information theoretically, given the noise, to obtain such a good overlap. Simply there is too much noise, the information got lost. Okay, the green region, that's where the approximate message passing gives us such an overlap given the noise. So that's easy, at least for this particular algorithm. And then there is an intermediate region where information theoretically we could get such a good overlap, but the algorithm is not giving it to us. So far so good. You tell me that's, so what? That's nice. We have some algorithm that has a region where it doesn't work, so maybe some other algorithm will work in that region. So this is like one point that is really interesting, that we actually believe that there is no algorithm, polynomial one, that will work in that region. So there is a conjecture that in the type of problem that I'm talking about, so concretely this one, but the class is kind of broader, here I list other problems where we identified exactly the same algorithmic barrier, that of all polynomial algorithms, this approximate message passing is the best one. So of course this is like as conjecture as it can get, because if I prove that, I would be on the way proving that P is not NP, and many other things that are impossible to, that nobody believes are simple to prove. So that's not going to be so easy, but it's giving us some interesting hint about where can we start building something like theory of typical or average algorithmic complexity. All the tools we have from the computational complexity reductions kind of, are not easy to use in this case, because the ensembles don't reduce to the same ensembles of instances. So it's a very intriguing, say, theoretical computer science kind of conjecture and track to follow. But that's not what I want to be talking about. That's the last slide about, it's not quite last about the hard phase, but I go back to my end question from the beginning. Because now I gave you somehow summary of last couple of years when we were working on these problems, getting some progress. But I want to concentrate on this second part of the question. How do widely used algorithms compare? So this approximate message passing is nice because we can analyze it. So that's why we love it. We can prove theorems, but basically nobody uses it in practice. It's kind of fragile towards the assumptions on the randomness, and it has some promises, but it's not quite there. So what are the widely used algorithms for non-convex high-dimensional optimization? So that's a quiz for you. Which algorithms these days are the ones used everywhere for non-convex high-dimensional optimization?
Can we find answer by Googling?
Say it again. No guesses? Yes? Good. Gradient descent. So for those of you who don't understand why he's saying that, I have a hint. What is the algorithm that is used to train these deep neural networks? It's gradient descent-based algorithms. And yesterday over lunch, Cyril told me that maybe not everybody will understand, that that's the case. So I decided to explain machine learning in 5 slides. So crash course on machine learning to kind of tell you why, in which context these gradient descent algorithms are used, and what we want to understand about them. So the task of machine learning is to, typical task of supervised learning is to classify pictures of cats from pictures of dogs. Every human and kid can do it. It's easy. What does it mean for a computer, right? How does a computer see a picture of a dog? So it's this long sequence of 0, 1s. They are grouped into triples for the 3 different colors, and each of the elements in that triple represents the intensity of the color at that given pixel. And now neighboring pixel probably have similar colors, so the neighbors do not change so much one from another. And then there are complicated correlations in all that tell you whether it is a cat or a dog. But you see, if I show you this sequence of 0 and 1s, it's not easy to see from the sequence whether it's a cat or a dog. If I don't give you the way to translate it back to the figure, you will have no idea what to do. And that's what the computer has to do. The computer has to find a function parameterized with some w, so that if on the input of the function you put this long sequence of zeros and ones, it outputs either +1 for a cat or -1 for a dog. This, of course, is a choice, but something for a cat and something for a dog. And 15 years ago, we had no clue how to do this with some decent performance. These days, these deep neural networks do it. Every student can download TensorFlow and do it in like 1 hour on their laptop. So how does this work? It's very simple, actually. Like probably all of you at some point in lycée or something saw linear regression. So linear regression is a special case of a neural network, if you want, the simplest one, where this function fw, the ansatz for this function is simply that it's a linear scalar product of the input times a vector w. And the goal of linear regression is to adjust this w so that the output corresponds to what you're seeing on the images on which you are training the network. So that's linear regression. And when you are fitting points by a line, that's exactly what you're doing. You can generalize this slightly, especially if you want to go to these +-1s instead of real outputs, that you put here some nonlinear function phi, for instance, the sine, to get to +-1s. So that's still like statistics, I don't know, 40 years ago, you knew how to say things about that. Neural network is just a simple generalization of that, where you multiply the input by this time a matrix of weights and you apply nonlinearity component-wise. And then again, you multiply by a matrix of weights and you apply a nonlinearity element-wise, and you do that a couple of times. And we represent it by this kind of picture. And the number of times you did it is the number of layers. And the deep in the deep learning refers that the number of layers is kind of largish. It can be like hundreds, but here it's 4. So it's just a special form of an ansatz for the function by which we are fitting. And how is, so now the whole art is how do we choose, how do we adjust these w's so that it works? And also that is actually extremely simple. The way these days these w's are adjusted is probably the simplest possible thing one would think of is that one defines some loss function, but you can think of the good old least squares, simply taking the output minus what the function currently gives you squared and summed over all the examples. People use other ones, but this one is as good as the others. And you're trying to minimize these loss functions with respect to these w's. This is like tremendously non-convex, horrible function. So this, the straightforward thing that you can do is to do gradient descent on the w's. So you simply compute the gradient, go a little bit in the direction of the gradient, recompute it, etc., etc. And if you have many labeled examples and many GPUs, this works. It's as simple as that, no magic there. So, okay, good. So, why did we need wait to, 2010 to actually make that work? Well, that was mainly in the labeled examples and the GPUs. The ideas on the math side were there a long time ago. So what do we know? One slide on the theory of neural networks, what do we know and what do we don't know? So we know that this function is general enough, that this ansatz is actually a universal approximator, meaning that there exists a set of w's that any function you might be possibly interested in gets well approximated by this ansatz. So that's a good news. This is not obvious, right? But these are good old lizards from theory of learning. But unfortunately, we also know that finding those w's is an NP-hard problem for even very trivial examples of neural networks with 3 hidden neurons, or there's this paper which is the classic paper on computational hardness of this. So what we don't know in particular, of course, in practice these things are trained and good w's are being found, but theoretically we have no clue when the optimization problem is actually tractable. What are the rules, what are the conditions, the magic properties of the data and the network and the function, so that this problem actually computationally is not as hard as the worst cases, but is actually tractable. This we don't know, and many other things related to it. So, okay, with this crash course on machine learning, now you kind of realize that understanding what the gradient descent is doing in high-dimensional non-convex landscapes is kind of important thing to progress in this big question. So that's what we try to do in a variant of our guard game. So before going there, let me just remind you what are the gradient-based algorithms on which we got some results. So this will be the two ones that are probably most widely studied in many areas, but notably in physics as well. There's the gradient flow algorithm, where you simply take a derivative of the loss function, you add there a weight decay constraint or spherical constraint, as we call it sometimes in physics. And for the gradient flow, this t here is 0, so there is no noise. And the other version will be this Langevin algorithm, where you put a noise of a given variance that is proportional to what in physics is the temperature. And if you set it this way, the Langevin algorithm has this nice property that you can prove that at large times, but unfortunately in the worst case exponentially large times, this algorithm will be sampling the posterior measure. And before we saw that sampling the posterior measure, that's the right thing to do to obtain the base optimal estimator. So we want to do that, that's a good thing. But the question is, can we do that actually in large constant time, or linear in the size of the system, or constant per input dimension? Because if we can do it only in exponential time, we don't care. Practically, we don't care. So that's what we would like to understand in some model where we can actually understand it. And what would be such a model? So in the neural networks, in this deep learning, we are very far from that. So can we cook up such a model? So this is kind of a model of the list of ingredients that the model should have. Okay? So first we want it to be high-dimensional, non-convex, and kind of noisy, that we cannot like trivially recover exactly what's going on. But that's kind of the obvious requirements. Then there are these two requirements. So this one of the general, the second one, that's something. We want to keep the property of this machine learning, because the way I explain it to you, what you actually want in machine learning is that if I present to you a new picture of a cat or a dog that was not in your training set, you want the function to work on that picture, to give you the right label. That's what you actually want. You don't really care about getting a good value of the loss function that you minimized by the algorithm. That's just the means to get to this good generalization error. It's not really even obvious why that should be the good means. It just happens to be the good means, right? So we want to stay in this spirit of a problem where we have some notion of good that is independent of having a low loss. Okay, so this is really important, because this, the interplay between the two seems to be at the basis of why, there are these mysteries in how deep learning works or doesn't work. So we want to keep this property. So you will see in a moment how we are doing that. And crucially, we want to have a model where we can analyze what the gradient descent and the Langevin dynamics do in some closed form that we can actually understand. So this one, of course, is the hardest one to. If I didn't put the fourth one, you have like any kind of neural network would satisfy these, is a good model, but the fourth one, of course, is a difficult constraint. So the model on which we managed to do that is actually, again, that's why I started with this card game, a variant of our card game. So which variant this time? I have a deck of cards so I need to know the size of the system so that the deck of cards, the elements are distributed according to a Gaussian with a variance such that the sum of squares of the cards is 1. They live on an n-dimensional hypersphere, and this is how I generate my deck. So it's not a big deal. I just take Gaussians, rescale them with properly so that they are on high-dimensional sphere. So there's the cards, and then what do I observe? I observe the product plus a Gaussian noise with variance delta 2. So remember the delta 2, because all my figures later on will be in terms of delta 2 and delta p. So I observe the matrix from all pairs, and I also observe the tensor from all triples. My pictures later on will all be for pairs and triples. So the p will be 3. Okay, so not much changed. If you understood the game, you understood this model. And the goal again is I observe this matrix and the tensor, and I want to recover back the ground truth value of the card. And that's my goal. Being close to the ground truth, that's the ultimate good. But then I will be solving the problem by transforming it into the optimization problem with the loss function that is this Hamiltonian, that's just the logarithm of the likelihood. And minimizing that log likelihood, will be what I will be trying to do algorithmically with the gradient flow. But that's not the ultimate goal. What I will be interested in, whether the minimum lies close to the ground truth or not. So this is this distinction between the pure optimization problem and a problem where I have some good notion of this generalization here. And in physics, this happened to be a mixed 2 plus p spherical spin glass model for those of you who are familiar with that terminology. So first thing I show you is just the application of the first part of the talk. Like, what is the Bayes optimal estimator able to do here? And what does the approximate message passing algorithm do before going to the Langevin gradient flow? So this is the slide that you have already seen here. I just explicited this free entropy for that particular model. That is a really simple expression in this case. The fact that the deck was drawn with Gaussian distributions, I can do all the integrals by hand. It really gives me this trivial expression here. It's very easy to see how many maxima this has, and I can plot anything I want. And the phase diagram I get from that is the following. So here is the noise I'm putting on the tensor, and here is 1 over the noise I'm putting on the matrix. So in the corner up there, both the noises are 0, so that's a very easy corner. And in the corner here, that's a corner where both of them are very big, so that's clearly the ground truth will not be possible to recover it because it's just flooded by the noise. Then there is this line. When the noise of the matrix is smaller than 1, so if you only had the matrix, that would be the good old BBP phase transition, the one of the spectral method. So above it, even if you only had the matrix, you actually can get some correlation with the ground truth. So here the different colors are telling me, can I or not get some correlation with the ground truth with respect to something completely orthogonal to the ground truth. So above, even if I only had the matrix, I can do it. And not surprisingly, the approximate message passing can do it. Can get actually optimal estimator in that region. In this red region is impossible because the noise is just too big. And this orange region, that's our hard phase where it's information theoretically possible, but the approximate message passing is not able to do it. Okay, so that's just the same story on a slightly different problem. But what I really want to show you now is how in this same diagram does the gradient flow and the Langevin dynamics. So that's the core of the message that I want to pass today. So back the slide of how I define these two. But how do we analyze something like that? That's a very complicated problem. So, well, at least my own strategy is to fish in old physics literature, so that often works. So this time, the paper that we needed to fish to actually understand how to analyze this is this paper by, maybe that's not the first one, but definitely it's like a very nice one where you can actually understand what's going on. The one of Kouliandolo-Kurjan, that is kind of a landmark paper that helps us understand how the dynamics of glassy materials, such as the window glasses or spin glasses, are actually behaving. So it's a very well-known paper in the physics of glassy materials. As far as I know, nobody took this methodology developed there to actually describe how algorithms are working. So that's kind of what we brought. They derive equations. I will show you our version of the equations for our model on the next slide. But for this particular paper, they don't have the ground truth there. They don't have the spike. Otherwise, it's the same model that they deal with. So for their model, that the equations are actually rigorously correctly describing the dynamics, there is this paper by Gérard Benarous and Amir Dembo and Alice Guillaume from 10 years ago or so, 13 years ago, that are proving that this is correct. We haven't done that proof for our equations yet, but that's a job for somebody who feels confident about reading that paper and generalizing it to our case. So this is how the equations that are describing how the Langevin this is the t=1 case and t=0 case, so I'm just showing you both of them, they look very related. So this is a set of integral differential equations that are describing in a closed form when n is infinity already of what is the properties of the gradient flow and the Langevin algorithm in terms of three quantities. So the most natural one is the C bar, which is the correlation with the ground truth. That's what you care about. That's the correlation the algorithm gets at time t. So that's one that you care about. But to write a closed equation on this one, it actually will depend on two other ones. So you need three equations to have these, to describe these three quantities. This quantity is a correlation between two configurations. The Langevin or gradient flow is sampling at two different times. And this third one is a kind of a response function. If you perturbed everything a little bit at the beginning, how would the dynamics change? So you define these three quantities. This is just the definition. And then you work a bit hard to realize that you can write a closed set of equations on these three quantities. It's still not like a very easy to solve set of equations, right? We can solve them numerically. The n is infinite already, so this is already in the thermodynamic limit. But it took us a few months to set up the code properly so that we get a solution that we trust that it's precise enough and correct. But so we did that. Yeah, I will show you later on that we didn't need to do that actually, but we did that. And this is an example of how does the Langevin algorithm work. So to walk you through this figure, this is, as a function of the time, what is the correlation with the ground truth? For the different curves are different values of the noise on the tensor. So first, the inset would be for the AMP algorithm, and there everything is very intuitive. As the noise is getting smaller, the correlation is getting better. So as the curve is getting lighter, the correlation is higher. And the curves are not crossing in any way, so that's kind of what you would expect. With the Langevin algorithm, the lighter curves end up higher, actually at the very same values as this AMP. It's aiming to compute the base optimal estimator. When it succeeds, it actually succeeds. They both agree. But what is striking here is that for the lower values of the noise, for the Langevin algorithm, it takes longer to get there. And that's very strange, because as noise is getting smaller, things should be simpler. It should realize faster that it can get where it's supposed to get. But here it's exactly the opposite. As the noise is getting smaller, it takes longer. So that's kind of a surprising thing. And if you if you actually realize that if you draw these times, they do appear, numerically to diverge at a certain point, and if you kind of do these extrapolations and collect the points where they diverge, you get the following line in the phase diagram. Is the same one I showed you before. The approximate message passing was working in this green region, but the Langevin algorithm is working only in this region up there. So when it is working, it's getting the same marginals as the approximate message passing up to, I don't know, many digits. But in this region here, when the noise of the tensor is small, kind of counterintuitively, it doesn't work. Why? I will explain, but in one sentence, because this is kind of very counterintuitive, it's because it's the tensor contribution that makes the landscape very complicated and that makes the algorithm stuck. So if you actually ignore the tensor, you would do better. But if you keep insisting on having the tensor there properly so that asymptotically you would sample the posterior measure, it actually hurts you. So we were not expecting that. We thought that these two lines will just be the same. So you're very surprised by this fact. So that's for the Langevin algorithm. Now I can do the same for the gradient flow. So while the Langevin algorithm is really aiming to compute the base optimal estimator, the gradient flow is not doing that, right? It's minimizing the likelihood, or maximizing the likelihood, sorry. And it's just a means to perhaps get a good correlation with the ground truth, but it's not the provably best way to get there. So it's not surprising that it actually does slightly worse than the Langevin. That's not surprising, So we do exactly the same for the gradient flow, and we get this line that is yet still above the Langevin curve. So the gradient flow would give us some good correlation with the ground truth in this region and nothing below, zero correlation below. So the fact that it's worse is not surprising because it's kind of going after the wrong objective, although this is what we usually do in machine learning. So now there will be another mystery. So what is the usual explanation, kind of the cartoon that people have in mind, to explain that gradient flow would be working in some region of parameters and not working in others? So it's kind of a picture that looks like this. As you're increasing the signal to noise ratio, if the signal is too weak, there is some like minima here, the blue one, that corresponds to the ground truth or close to the ground truth, something you want to find. But if there are many spurious minima next to it, higher up in the loss function, lower maybe perhaps in the loss function, with big basins of attraction, the algorithm would get stuck there. And it will get stuck there and stuck there and stuck there. And only at the point where there is truly really the only one, the global one that corresponds to the ground truth, it will actually go there. So that's kind of the usual cartoon. So in this model, we cooked it in a way that we can quantify this picture very precisely via the Castros approach. So what we can compute here is the logarithm of the expected number of local minima at a given value of the loss and at a given correlation with the ground truth. So this is how the expressions look like. They're a little daunting. But from these expressions, I can extract very easily this trivialization transition. That is, when in the landscape there really only is the good global minima and there are no spurious ones anymore. And that's this following line, the purple line, the landscape trivialization. And here is another surprise. This landscape trivialization line is not describing what the gradient flow is doing. The gradient flow is actually working also in this region, where we can prove that there are spurious local minima, and it's happily ignoring them. So how is that possible? So this kind of trivial cartoon explanation is wrong. It's not working, at least in this model. So what is going on? What is the right cartoon explanation for what's going on? Is the following cartoon. So what's actually going on is that the gradient flow happens to get stuck in the highest and widest minima. The fact that they are highest and widest at the same time follows from the Castros formula. So that's reasonable to expect that you will get stuck in those. If they are at the same time the most numerous and the widest, that makes sense that they attract actually the randomly initialized dynamics. They get stuck there, and what matters then is not whether there are still spurious local minima lower or not. What matters is when these minima in which the algorithm gets stuck, whether those get unstable towards the signal or not. And again, the instability of the minima in the Castros approach, we have a hand on it because they just are there negative eigenvalues in the corresponding Hessian that go in that direction or not. So this is something that we can quantify from the Castros approach. And instead of getting this line where everything is trivial, the right line is this one, when the highest ones get unstable and the algorithm then flows along this direction to the solution, while there were many spurious minima higher in the loss function, but it just completely went around them, ignored them. So when we plot this line, it looks like, oh, no, I plotted in the next slide. Okay, this is just, we can get this line in several ways. And this is just one slide where we distilled the simplest recipe to get to that line, to the analytical expression for that line, which is this very simple expression just in terms of the delta 2 and delta p. And to get there, we need to compute what's the overlap at what we call the threshold states. There's the highest ones and widest ones. That's an expression that, in the spin glass literature we call the replicon condition. So that's again an expression in many of the papers 40 years ago. 10 minutes, perfect, at the end. And the next equation we need to plug this into is the state evolution of the AMP, because that tells us something about the instability in the direction of the signal. So it's just really these two very simple equations, putting, fixing this Q here to the Q threshold and looking when the M here starts to grow or not, if we perturb it away from 0, gives us this condition. And if I plot this condition in my phase diagram, there's the blue line. And the points, those are the points that we painfully obtained by working basically half year on numerical solution of these horrible integral differential equations. And okay, they seem to agree. So that would be for the gradient flow. And you see the landscape trivialization is a different line. And now the same, this argument was for any temperature. So it's just a matter of plugging here a 0 or 1 to get the figure here. There's the green line here. Is again perfectly going through the points that we obtained by numerically solving the equations. And here there is a really simple equation. There is actually another critical point here at 2, where this line gets to 0. So that's kind of interesting. So I will be stopping here, just concluding that in this, what we called mixed spiked matrix tensor model, we can analyze gradient flow and Langevin algorithm, and the gradient flow is worse than the Langevin, which itself is not surprising, but what is surprising that they are both worse than approximate message passing. And a really interesting open question is, how should we tweak them? How should we change them? What should be done so that the gradient-based algorithms actually reach the same threshold as the approximate message passing does? The other point is that the gradient flow sometimes works even when the spurious local minima are present. So, this long line of works in computer science where people try to prove that in certain regimes of neural networks there are no spurious local minima. We need to keep in mind that this is just the upper bound, that these algorithms actually can work, and experimentally we know that they work even when they are spurious local or global minima. So this is, some hint of why this could be so. And we have this close expression based on the threshold states and their instability that we think is applicable beyond this present model, because we picked this model to be able to write these Coulomb-de-Locourchan equations that are very particular to these spherical mixed spin glasses. But we also have, simple models of neural networks where we don't know how to write those. But we can totally, repeat this recipe. That's easy to do. That's like something. So we are working in that direction to understand whether in the other models it's still actually describing what's going on, or if there's just some coincidentally true in this model, but not true in general. And kind of, I hope I showed you that statistical physics has many useful tools applicable in high-dimensional inference and learning. And with that, the last slide, it is just a list of papers on which this talk was kind of broadly based, if you want to go into more details. Thank you.
Thanks very much for a great talk. Are there any questions? Robin.
So you were saying that this the algorithm works even when sometimes when there are spurious local minima, and so you have a pretty convincing explanation because you have a mechanism and then you have that plot that seemed to correspond with it numerically. So I'm wondering though, if you know for sure in that region that there are spurious local minima, because the Katz-Rice formula will give you the log of the expectation, but not the expectation of the log.
That's,
so
a very good question. Something I put under the carpet during the talk. But in that last paper, so we actually computed the quenched complexity of the Katz-Rice formula. We can do that. I mean, we did it generically. It so happens that when the correlation with the spike is 0, the annealed and quenched coincide. And so the annealed one that we, the line that we get is purely driven by what's happening at 0 correlation. So in that case, actually, there is no difference coming from the difference between the annealed and quenched. But you're completely right, I didn't explain that. And in general, the annealed would just be an upper bound. But that's not the case in this model.
More or less on the same topic, that is when you have this intermediate phase with a small gradient that drives you to the good minimum. And I think I posed a similar question to the student of Guillaume when it was the seminar. Suppose that you start a statistics of searches with gradient flow in parallel from 1,000 random points. And when you are a bit stuck, you have your gradient that is going towards the wrong minimum. Also, morally, you have a small gradient also towards the true minimum. All the other 999 independent rounds, each of them are stuck, and each of them has its small signal towards the good one. If you now make the average of all the gradients, maybe this number of runs in parallel will enhance the signal and will allow you to go a bit faster, a bit farther in the phase diagram.
So that's a again, good remark. There is a paper by Giulio Biroli and Chiara Cammarota and Federico Ricci-Tersenchi. They call this kind of the replicated algorithm, that is showing that this is a strategy that improves the performance. But it's in a different model, and we are not yet sure that in this one this would actually, this effect might just, everything is high dimensional and everything concentrates exponentially. So it's not clear whether you would need exponentially many of these replicas or if just small number is enough to actually get that effect. So that's okay. That's like, when I had my question, how can this question up there? How can these algorithms be improved to reach the MP threshold? What are the generic strategies? This could be one of them.
Okay, maybe I can ask the dual question about that. So the other sort of natural idea is how can we export approximate message passing into deep neural networks?
Yes, so that's a very good question. So in like other, in slides that I didn't include in this talk, I kind of have a summary of where we are in that. So there are two main troubles in doing that. One is that if we want to write, so you can always write heuristic way of writing something similar than approximate message passing, then you can do, experimentally, empirically, I don't know, anything, right? But if you want to stick to the approximate message passing that asymptotically gives you the optimal thing, asymptotically samples the posterior, whatever it means, then currently we can only deal with neural networks where the dimension and the number of samples are both large and the ratio is fixed, so that's a very reasonable limit, but the number of hidden units of order 1. That's not a reasonable limit, okay? So we are restricted to that, and if the number of hidden units is also extensive, then we don't know how to, we don't know how to do even the non-rigorous third replica calculation. It's a challenging case. That's one reason. And another reason is, as the kind of, I think why gradient descent is winning, because it's so super robust to pretty much everything. Whereas the approximate message passing, it's great to get theorems on these simple models, but it's very sensitive to the randomness that we assume. And if there are some correlations, it very fast stops converging. So there are versions of approximate message passing, notably something called vector approximate message passing, that are much more robust, and people are actually testing those on real problems. But so far on problems more like sparse linear regression, I worked with people, for instance, that do brain imaging. So there we could get some interesting speed up with respect to the algorithms they were using. But for training deep neural networks, the speed and the lack of robustness and the fact that we don't have them for the large networks anyway, maybe one day, but I would say we are far from that.
Thanks. maybe I can permit myself one more slightly more technical question. I seem to recall Gérard Benarous telling me about a paper of, I think, Polinsky and Zupelius, which has some phase diagram for the Langevin dynamics, or describes sort of what it converges to. So does their picture agree with your picture?
No, that's a related kind of line of work, but for the problems that are not this spherical mixed p-spin, we can kind of go partial way in deriving these equations, but we will not get to the, maybe some of you didn't find them nice, but those equations were nice and closed and we can solve them reasonably. Whereas in these papers on really neural networks, they got a set of equations that are somewhat self-consistently closed but are nightmare to solve. So whereas here we can numerically be confident up to times 10 to the 6, with those maybe 50, So this is, you cannot really probe very much what's going on at larger times. But that's if we want to write, that's exactly this third point, right? That if we want to write these full dynamical mean field equations. But from what we got in this model, it seems that maybe we don't need that to get those lines. So that's something worth probing, and we are looking at that.
Okay, if there are no further questions, thanks again for an excellent talk.
Thank you.